What if I ask my friend there the size of the leaves, the taste of the leaves? Are they all the same? Now, who knows where my friend is headed next? In fact, just like my own lack of knowledge on what's going to happen next, physics has long abandoned the idea of determinism, the idea of certainty, and in fact, the world as we know it is uncertain. Now, this uncertainty could be in part due to our own lack of knowledge of things, for instance, in this particular situation, or it could be at the heart or the very essence of the way nature just is. What we need at our end is a mathematical language to characterize and understand this uncertainty. The uncertainty principle at its heart is exactly this. It's one such relationship between the range of values of two what are called random variables and how this range of values is constrained in certain ways. So before we really understand the uncertainty principle, we need to define and understand what a random variable is and how do we compare it with what would be a sure variable. So that's the plan for this part of the video. So let's get to defining what a random variable is. So a quantity that under a given condition can assume different values is what we define as a random variable. For instance, let's say you have an unbiased coin. You flip the coin and you keep all the other conditions exactly the same. What we'll observe is that sometimes the coin lands with a face showing heads and sometimes it shows a face with a value of tails. Thus, the outcome of a coin toss is different even though we may have performed the coin flipping in exactly the same set of conditions. Thus, the outcome of a coin toss is one example of what we call a random variable. And you can think of many such different examples of what are called random variables. I encourage you to think of a few more examples. As a notation in mathematics, we denote a random variable with uppercase letters. For example, a capital X, a capital Y, capital W, a capital Z are how we denote a random variable. And the set of values that this random variable takes can be denoted by small letters. We'll talk more about this in the next slide. In contrast to a random variable, a sure variable will give us exactly the same value if we perform the experiment under the same set of conditions. Now, it can happen that for a given experiment, we might be able to define both a random variable as an observable and a sure variable as an observable. For instance, let's say instead of being interested in what face does the coin show upon landing, we are just interested in throwing a coin vertically up and measuring the height to which the coin ascends under a uniform gravitational field. In this case, if we know exactly the initial speed which we impart to the coin, and if we know the gravitational acceleration, for instance, if we are doing the experiment on Earth, we can precisely predict to what height will the coin ascend. And in this case, the height that the coin ascends can be what we call a sure variable. Now notice one thing, that sure variables are basically an idealizations of reality, where we are ignoring any kinds of fluctuations or random effects which might happen and which do happen in any real experiment. So in that sense, random variables are a more general class of variables, and sure variables are conceptually simpler to understand, and they could be considered as first approximations or good approximations to reality under certain conditions. But the random variable, or a definition of a random variable, encompasses both randomness and cases where randomness is not present. And in cases where randomness is not present or where we are ignoring the randomness, we can define what is called a sure variable. Notationally, we typically use lowercase letters to denote sure variables. Now, since a random variable can take on different values under the same set of conditions, we might be interested in knowing what is the likelihood of each of these values to show up if we perform an experiment. Or we might be interested in knowing what is the expected outcome of an experiment. Now, random variables can also occur in two different kinds of species. One kind of a random variable can take on only specific sets of values, or it can take on values from a finite set of values. For example, the coin toss that we have been talking about can only display either a heads or a tails. By the way, if the coin is thick enough, it can also land on its edge. But in these cases, we're ignoring sort of this edge effect. And as you can see, I'm already making some approximations even when I'm defining the coin toss experiment. So coming back to the main point, random variables that take on values from a finite set of values are typically called discrete random variables. On the other hand, we can also have a random variable which can take on a continuum of values. So for the purposes of this discussion, we're going to focus our attention only on random variables which can take on a finite set of values. And then coming back to the main point, which is, in order to fully characterize a random variable, not only do we need to know the range of values that it takes, but we might also be interested in knowing with what likelihood or with what probability does it take on each of those values. So for instance, for the coin toss, what is the likelihood that we observe a heads, or what is the likelihood that we observe a tails? Now, how probable the different values of a random variable are is quantified by assigning to each of those values a real number between 0 and 1, and that real number is what we call the probability of that particular outcome. Now, the probability of the outcomes satisfies two very important properties. First of all, the probability of any particular outcome lies between 0 and 1. It's any real number between 0 and 1. By the way, if the probability of a particular outcome is 0, then that outcome never happens. And if the probability of a particular outcome is 1, then that is the only outcome which we'll observe. So in this sense, an outcome with a probability equals to 1 becomes a sure variable. And just like we talked about earlier, a sure variable is a specific case of a random variable, which we can quantify through the use of probabilities. So coming back to the two important properties of what a probability satisfies, the probability of any particular outcome lies between 0 and 1. Secondly, since amongst all the possible set of outcomes, one of the outcomes definitely occurs during a specific trial or an experiment, it turns out that the sum of the probabilities of all the outcomes should be equal to 1. These are the two essential properties of the probability of the different outcomes of a random variable. Just to summarize, a random variable now is completely characterized by the range of values or the set of values that it takes and the associated probabilities of each of those values. The next important question is, how do we actually establish what the probability of each of the outcomes of a random variable are? In other words, how do we assign a real number lying between 0 and 1 to each of the particular outcomes of a random variable? Now, it turns out that this question doesn't have just one answer. Two very common approaches to assigning these probabilities are what are called a Bayesian approach and a frequentist approach. So let's look at the Bayesian approach first. Now, a Bayesian approach typically assigns probabilities based on some prior knowledge that we have about the system that we are investigating or the variable that we are looking at. For example, we might believe that in the coin toss experiment, the coin is perfectly fair. It's thin enough that we'll only expect either a heads or a tails, and that it's fair. And by fair, what we mean is that if I toss a coin, it is equally likely for it to show either a heads or a tails. Now, in order to quantify this idea of equal likelihood of the two outcomes, we might say that the probability of observing a heads is equal to the probability of observing a tails. And what that really means is that it's equally probable or equally likelihood that we can see a heads or a tails. If this is true, and we use property 2 of probabilities, which is the sum of probabilities of all the possible outcomes should be equal to 1, we'll see that the probability of heads is equal to probability of tails. Therefore, probability of heads plus probability of tails should be equal to 2 times the probability of either of these events. In other words, the probability of a heads or a tails will just be equal to half, which is 0.5. And this agrees with our everyday intuition of probabilities, which says that when I toss a coin, there is a 50% chance of me observing a heads and a 50% chance of me observing a tails. Supposing, however, I do not have a good intuition about what I should expect out of an experiment. So for example, in the coin toss, maybe I have no idea that it's a fair coin, or I just do not have any intuition that it's equally likelihood for me to observe both a heads or a tails in a given experiment. The other approach is what we call the frequency or the frequentist approach to establishing the probabilities of the different outcomes. And in this case, the experiment is fairly simple. The way of determining these probabilities is fairly simple, although laborious. All we have to do is take the coin and toss it many times and record what we observe. Once we have done this experiment, let's say for simplicity we do it 100 times. We toss a coin 100 times, and for each of those coin tosses we record whether we observe a heads or a tails. Let's say we denote the total number of times we toss the coin as capital N, and then we denote the number of times we observe a heads as N brackets heads, and the number of times we observe a tails as N brackets tails. Now we know that on a given coin toss we observe either a heads or a tails. Therefore, the number of heads plus the number of tails should be equal to capital N. That's the total number of trials. And now we can establish the probability for heads as being equal to, approximately rather, being equal to the number of times we observe the heads divided by the total number of trials we did. And I'm using the notation approximation here because technically the ratio of the number of heads to the total number of trials is what is called the frequency of the number of heads, and only in the limit that we perform very large number of trials would this frequency approach the theoretical value of the probability of the number of heads. So we'll ignore these complications for now, and we'll say that the frequency or the number of times we observe a heads divided by the number of trials we did is approximately equal to the probability of heads. Similarly, the number of times we observe tails divided by the total number of trials we did is approximately equal to the probability of observing tails. Now notice, just inherent in this definition is the fact that the sum of the probabilities for heads plus the probabilities for tails equals to 1. Having fully defined a random variable in terms of the range of values it takes and the associated probabilities for each of those values, we can now extract more information, more measures from the random variable, which proves useful in us interpreting how the random variable plays out. One example of this useful measure is what is called the expected value of the random variable. An example of the expected value is the mean of a random variable. Now, before we get to mathematically defining the mean and other expected values of a random variable, it's very important and useful for us to recast the set of outcomes that we observe for a particular random experiment or a random variable in terms of numerical values, because that allows us to use those numerical values in calculations. For example, in the coin toss experiment or in the coin toss scenario that we have been talking about, a coin will land on a face which will show either a head or a tail. Now, a heads or a tails is not a numerical value, and as you may have reflected upon in the way we have designed the slides, it's often cumbersome to actually write probability of the random variable taking the value x equals heads or x equals tails. So it's very useful, and you'll actually encounter this in many situations, that it's often very useful to recast these values, these labels, into numerical quantities. As an example, I'm going to call heads as +1 and tails as -1. Now you could choose any other numerical value. For example, you can call heads 0 or tails 1, or you could call heads 100 and tails 300. It's up to you. As long as you're consistent in your calculations and you know what numerical value you associated with each of the outcomes, we are okay. With these numerical values, I'm going to now define the expected value, or actually one example of the expected value of the random variable, which is the mean of the random variable, in terms of the equation that I've written on the slide here. That is, the expected value of the random variable is the summation of the particular value that a random variable takes multiplied by the probability with which it takes that value, and you sum it over all the values multiplied by their respective probabilities. For example, for the coin toss that we have been talking about, with heads identified with the numerical value +1 and tails identified with the numerical value -1, we find that the expected value turns out to be +1 times the probability with which it takes the value +1, and that's 0.5, plus the other value it takes is -1, which is what we have labeled tails as. So -1 times the probability with which it takes the value -1, which is again 0.5, and we find that the expected value, or the mean in this case, is just 0. Now, if you had labeled heads and tails with different numerical values than the example that I'm showing here, you will get a different expected value, but that's okay as long as we are consistent with it. One interesting thing about the mean, the way we have calculated here, one interesting feature that comes out rather, is that the mean of the random variable, or in general any of the expected values, need not be or need not coincide with any of the specific outcomes that we see during an experiment. For example, in this particular case, the mean turns out to be 0, which is neither +1 nor -1. It's neither of the values that the coin toss actually gives us, but nonetheless it's a measure of the behavior of the experiment that we're talking about. It's somehow measuring the fact that if you do multiple coin tosses, overall what you'll see is an equal likelihood of +1 and -1, and therefore the mean, if you were to think of this as money that you make in a coin toss, maybe +1 if you win and -1 if you lose, you'll find that the expected net money that you earn is just 0. Now, there are some other notations for what we define the mean of a random variable as, and some of these notations I've just written at the bottom of the slide. So for instance, you might see the random variable x with an over bar. That's again a convenient and often used notation to denote the mean of a random variable. Or you could just place the random variable x in angular brackets, and that's another common notation you'll see. Another example of an expected value is what is called the variance. In fact, we can define many different kinds of expected values of a random variable by inserting that random variable in some or the other functional form. So in the first equation on the slide, you can see that I've defined a general expected value of a function of a random variable as nothing but the summation of the function evaluated at specific outcomes of the random variable multiplied by the respective probability with which that particular outcome occurs. Now, one example of the expected value of a function of a random variable is the variance, and the variance is defined through the function which looks like f of x equals x minus the expected value of x whole squared. So all we have to do in order to evaluate the variance of the random variable is we take each of the values that it takes. Again, please remember that we have recast all labels in terms of numerical values. So we take a specific value of the random variable, subtract the expected value which we have calculated before from that value, and then we square this. And with this, we multiply it with the probability with which that particular value occurs, and then you sum it over all values that the random variable can take. For the coin toss example, with heads identified with +1 and tails with -1, we find that the variance is equal to 1. Notice that the variance is the summation of all positive quantities, so it's always greater than or equal to 0. Now, as an interesting mental exercise, if you had a sure variable, that sure variable will always take one value. It will always give you one specific value if you repeat that experiment under certain given conditions. Therefore, the probability for that value to occur is just 1. Now, if you evaluate the mean of the random variable, or what we are calling the sure variable, you'll find that the mean coincides with the specific value that the variable takes. And it turns out that the variance is just 0. So in other words, the variance is somehow a measure of the variation in the data or the variation in the outcomes that we see around what we define as the mean of the random variable. And this is a very, very critical point which lies at the heart of the uncertainty principle. And this is what we're going to discuss in the next part of the video.